So we talked about the what, we talked about the why. Now let's talk about the how, the actual visual. How do we create a data visualization? How do we create a certain plot? How do we decide what to put on a piece of paper or on the screen? So if you look at the Tamara Munzner's model, so we'll talk about encoding, which is like the static, what it looks like statically, how to manipulate, and we will not go into the introduce, I think, but the most important is encoding here, right? That's the most important thing. When you create a visual, as with many different things, like for example statistical analysis, there's different decision styles, right? So one of them is, the first one is unintended design. So similar as to what a statistician may do, if a statistician only knows ANOVA, then everything that person will do, they will say, well, I'll do an ANOVA, right? If that's what you know, that's what you'll use. So basically, that's what's easiest to implement. Self-design is something like you do know a lot of different methods. For example, let's say in data analysis and machine learning, you know different ways of clustering data, for example, but you have no idea about the domain. So let's say, again, we're talking about genetics, but you have no knowledge about genetics whatsoever as a designer or as a data analyst. So you just make assumptions on what the user will need, about what the geneticist will need, right? Even though you have no idea yourself about the domain. That's called self-design. Genius design is similar, but you do know the domain. But you still haven't talked to the users, right? So you do know the domain. So for example, I have a background in genetics and genomics. If I get a genetics or genomics data set, I do have an idea of what may be useful, right? Even though I don't know what that particular user, that particular expert needs to do with the data, I already have an idea of what could be useful, right? So based on that, I can make some choice in what visuals to use, yeah? Which is one way of saying that I'm a genius, but that's aside. And then the fourth and the fifth one are really focusing on the user, right? So basically talking to the user and then knowing, okay, what do they want to do, right? So the task-focused design is short-term. So what do they want to, what tasks do they want to perform? Whereas a goal-focused is much longer-term. What do they want to accomplish at the end, and how can we help them get there? First looking at the static aspects, so the encode, right? Like I told you earlier, the task that someone does is always a combination of a verb and a noun, to compare trends, for example. Here's another very important concept, that your visual encoding is always a combination of a mark and channels, right? So remember the term mark, remember the term channel. Mark can be either a point, a line, or an area. That's it, right? So anything you see on the screen is a point, a line, or an area. And those can have different properties, like which are the channels. So could have different lengths, different angles, different volumes. They can have motion, different color. So hue is color, and so on, right? So those are the channels. These are things used to add to these marks, okay? And how do we decide what works and what doesn't work? Well, sorry, something else I mentioned first is that basically that all comes back to the semiology of graphics, which basically says the same thing, but I won't go into that here. But then the question is like, if we know our marks, points, lines, and areas, if we know all the different channels, color, size, width, saturation, darkness, and so on, right? Which ones do we choose? Which ones do we choose from that vast well, collection of options basically. And those decisions can be based on what's called Stevens' psychophysical power law, which basically maps out the link between the physical intensity of a signal and the perceived sensation of that signal. Right? So, like you see here, length has a value of 1, which means that if I double a certain, which basically means that we are pretty good at knowing if this is 1, right? If that is 1, I have to make sure it's in the camera, right? If this is 1, then this will be about 2, right? 1 and 2. I won't be that far off, right? So that works quite well because it has a factor of 1. Then brightness is 0.5, which means if I would increase the brightness in this room so that you would perceive it to be twice as bright, I'd actually have to increase the intensity of the light 4 times instead of 2 times, right? So that's a factor of 0.5. Then very interestingly, electrical shock is 3.5, which means a very small change in the voltage will have a very big change in the perceived sensation, right? And based on this, we have McKinley, that should be over there, right? I think in the 80s, made this overview. And if there's something I want you to print out of this course and put it as a poster above your bed, it's this one. Basically, what this shows you is that depending on the type of data, are we looking at quantitative data, ordered data, or categorical data, these are the different channels we can use, and it goes from good to bad, right? So quantitative data, position is really good, shape is really bad. Well, for example, if you have quantitative data, 0, 1, 2, 3, 4, you would not use like a triangle for 0 and a hexagon for 1 and a circle for 2. That doesn't work, right? I think you agree with that. I hope you agree with that. So that doesn't work, but position is really good. Eh? So basically where on your screen, and the good thing with positions, we have 2 of them. So we have x-axis and y-axis. So the position works really, really well. That is why a scatter plot is so effective, right? A scatter plot is really, really, really good for this reason, right? Going back here. The scatter plot is really good because we can measure the distance between an axis and a point as a length, and that's linear. So we basically are very well capable to actually identify where a certain point is. So position works really well. Ordered data, position works really well as well. Categorical as well. But we see, for example, hue, the color, is really good for categorical data, but it's really bad for quantitative data, right? So also, yeah, to mention here, so the distance, so to speak, between each consecutive combination is not always the same, right? So yeah, for example, slope and area, that distance may be, well, they may be more different. Where's my camera? Okay, they may be more different from each other than, for example, position and length, right? So hue is really bad for quantitative data, but it's really good for categorical data. And what I just mentioned, so position is really strong, right? We call that the power of the plane. Now, how can we use this, right? How can we use this, this overview? Let's say we have a 7-dimensional data set, right? And some dimensions are more important than others. And we want to make a plot. We can start with thinking about actually what is my most important dimension. Let's say that dimension is quantitative, right? It's numbers. It's a quantitative, so we start from the top, we use position. The second, the most important dimension, for example, is categorical. Categorical, well, we have 2 positions, so we use position again. The third most important dimension is quantitative again. Well, we cannot use position, so we have to use length. Right? And that's basically how you can make your choices. Basically, always start with position. Actually, we can turn this around as well and use it to analyze pictures. So if you have a picture, basically look at the position. What's the position of the things on the screen or on the paper? And that may be the most important thing that I want to show, right? Like I said, so color is not good for quantitative data, but still it's used a lot. Well, this is now older. It used to be new because these slides are from 2015. Well, some of them. So here we have average prices per municipality in Belgium, house prices. And it's the rainbow color scheme, right? So you go from red to blue. We know that they go from red to blue, but you have to know that, right? The reason why color does not work for quantitative data is, yes, color has to do with wavelength, right? So yes, technically, well, scientifically, wavelengths can be ordered. Wavelengths can be actually put next to each other, and then, okay, this wavelength, and there's that wavelength, and so on, right? But color is not the same as wavelength. Color is something that we interpret. Right? So we cannot say that yellow is more than green. That doesn't make sense, right? Or is green more than yellow? I don't know. Well, I don't know because the question doesn't make sense. The wavelengths we can compare, but not the colors. And looking at this picture again, remember one of the first sessions of videos in this series, I let you look at these things, right? So with that pre-attentive vision, so plots with all the blue dots and one red dot, and all blue dots and one red blue square here, right? Why did this work better than this, right? Because we're looking at two categories: blue versus red, circle versus square. Categorical, color, works better than shape. And that is why this works better than this. What does that also mean? Well, position is better. So what would be even easier than this is if you would have like a whole group of points over here and one point on the left. That would be even easier than this plot, right? Very briefly about color. So we could write a whole 2-hour lecture on color, but we won't do that here. I'll just very briefly go over the color space, like the color space that we use, right? But like I mentioned before, so color is something that comes from our visual system. It's not the electromagnetic spectrum itself, right? So we have to talk about color space and how do we describe colors. And you'll very often see red, green, blue used as a color scheme. So how much red, how much green, how much blue. It's useful, but not within data visualization. The problem is that there's this perceptual non-uniformity. So the distance between the colors, well, how we perceive the colors, is not the same as the actual Euclidean distance in that three-dimensional space. And also it's very non-intuitive. So for example, so this color, so this is how much green, sorry, red, this is how much green, this is how much blue. What is this? So what color is this? I have no idea. So apart from RGB, there's also other ones like HSV, right? Here we go. So, well, hue saturation brightness or hue saturation value, that's the same thing. And hue is actually the color, right? So that's a value between 0 and 360, and that one number represents the color, period. The saturation basically tells you well, how white it is. You go from the most bright color, like this very bright red, to white, right? And then the value is how dark it is, right? So there's still some shortcomings with that, but basically in data visualization, we mostly use HSV, hue saturation value, rather than RGB, right? There's other spaces as well, but I won't go into that. Basically, remember, color is complicated. Don't use RGB, and probably use hue saturation value. Something else that I want to mention here is the abstraction layer. How abstract do we want our visualization to be? So let's look at this system, which is the system of a car on a road. And the car just drives straight on, and the moment that it hits the curb, it will turn by 2 degrees. This is 2 here. I can zoom in. Voila. So it will turn by 2 degrees, and by just moving this slider along, you will move the car left and right? We can look at one abstraction layer higher and say, okay, why don't we just draw the line that car would follow, right? Instead of actually making the car move. And that's what this is. So we actually have the line here that car would follow, and then we can use a slider for something else, for example, by changing that angle, right? So in this case, it turns by 3 degrees. Again, we can take this, well, as we move this red line changes, right? So we can again take this one abstraction layer higher and say, okay, why don't we just draw all the lines, which is what this is, right? So these are all the different paths that a car could take depending on the angle that they will actually turn by. I don't know why these ones are outside the road. I'll have to check, but they are just, anyway, I'll have to reread the paper. Of course, this is still, well, we have here all the different paths a car can follow on a road with this bend in it, right? But what if we have a road with no bend or a sharper bend, right? That's what this is, right? So this shows the total overview of the turning rate and the bend of the angle, right? So if you look at one, well, this picture is the same as this picture, is the same as this picture. Voila. This is the same picture as we saw earlier. So we have a certain bend angle. So this angle is set of the road. And we just, if you look at this line here, basically that looks at a cross section across all angles that you can take. This is the opposite. So with a set turning rate, your bend angle changes. And if you look at one particular point, it's a combination of those two, right? If you look at this is a very literal representation. This is a very abstract representation. This is something that someone could understand immediately. Here you need someone explaining to you how to interpret this. I'll have to reread the paper again to remember what the red is and what the black is and what the white is. But there's something going on here, right? The thing is, if you are making a data visualization for an expert, or if you want to explore your data, if you want to explore the data, then it makes sense to work like this, even if it takes an explanation first, or if it takes a couple of seconds to actually understand what this means, right? Because there's much more information in here than there's in here, right? So here we're talking about abstract visualizations for an expert or for exploration. Here we talk about literal, more to convey a certain message